Hello there. In this lesson, we'll be learning about ionic compounds. So in a previous lesson, we learned about ions as being charged atoms because they have either gained or lost electrons. And there are a whole bunch of compounds that are made up of these ions. So a couple examples here are a snow melter, which is calcium chloride. And you've got table salt, which is sodium chloride. And you've got baking soda, which is sodium bicarbonate. And you've got this drain crystal thing, which contains some sodium hydroxide. And Epsom salts, which is magnesium sulfate. And you've got bleach around your house, which is dissolved sodium hypochlorite. And you've got some borax, which is sodium borate. And you've got your toothpaste, which has some sodium fluoride in it. So all those compounds are all ionic compounds, and we're going to learn in this lesson how to identify them and characterize them and make formulas for them. So a little review. Remember that some ions are cations, which means they're positively charged. You can see sodium here has 11 protons in its nucleus, and if you count the electrons around there, there's 10 electrons, which means it's got a +1 charge. And here's chlorine at the other side of the periodic table, and it has 17 protons in the middle, but with a full outer shell, that's 18 electrons, so it has a negative charge. So there will be an attraction between oppositely charged ions. Positive ones will be attracted to negative ones, and that's what makes ionic compounds, because these two like each other and they'll stick together. Okay, so the way in which ions stick together to form a compound is in what's called a lattice works. A lattice, fancy word for repeating pattern. So if this is a sodium here with a positive charge, then the chlorine will be next to it with a negative charge. And then there'll be another sodium next to that with a positive charge, and then a chlorine next to that with a negative charge, and then a sodium next to that with a positive charge, and so forth, right? And so you get this repeating pattern over and over and over again. And since it's all very uniform, there's like a symmetry to it. You get these nice symmetrical crystals. This is a magnification of some salt crystals, which are made of sodium and chlorine stuck together. And so ionic compounds, as a solid, make these nice crystalline shapes due to that repeating pattern that we call a lattice. Okay, so let's look a little more closely at how the atoms that make up ionic compounds form. This can be effectively done using Lewis symbols. So remember, Lewis symbols just show the valence electrons, and it's the valence electrons that are involved in bonding. So if you have a sodium ion or any metal, they will often give up their electrons when they get a chance. So we did this when we were coming up with their charges. They will give electrons up in order to become isoelectronic or have the same number of electrons as a noble gas. And so where those electrons go is often to another atom that would like to receive them. So the example here being chlorine. Chlorine has this space here because it needs one more electron to complete its outer shell. And so often it's a nonmetal that ends up accepting an electron from a metal. And so when that happens, that transfer means that the metal becomes positively charged, the nonmetal becomes negatively charged, and you end up with that attraction. They'll stick together, and you'll end up with your ionic compound. So ionic compounds are represented using formulas. Formulas use the symbols off of the periodic table, and they also use numbers to show the proportion of the different ions. So you remember that ionic compounds form that lattice, that repeating pattern of ions over and over again. And so in the case of ionic compounds, when you want to write out a formula, that's going to give you a ratio. That'll give you the number of each ion in the compound, the proportion of each, right? So in this case, the little number here means there are 2 sodiums for every 1 oxygen ion inside of this compound. And if you look at this formula here, that tells you that for every 1 aluminum ion, there's going to be 3 chlorine ions. So the numbers are always the quantity of each of the ions in the ratio. And if there's no number, you can assume that's a 1. If you write the element at all, it means there's 1. And then if you need more than 1, you put in one of these little subscripts. One last thing that's mentioned above here is that the metal, or the cation, always goes first, right? Always start with your positively charged ion, and then your negatively charged one goes second. Okay, so to be able to figure out the formula from the Lewis symbols, we can do a little bit of exchanging. So let's look at a couple examples here. So we have magnesium, and magnesium is in the second group if you have your periodic table around, which means it gets 2 valence electron. And then you got chlorine. Chlorine's in that 17th column, or group 7, which means it has 7 valence electrons. And so, as you recall, the metal, the magnesium, is going to give to the nonmetal, the chlorine. That's great for that first electron, and this chlorine now has a complete outer shell, so it doesn't need any more. It's now a nice chlorine ion. However, this magnesium still has an extra electron that it has to get rid of in order to ionize. So what happens is another chlorine, these chlorines are not all by themselves, there'd be cajillions of them. And so if you put in another chlorine there, well, it can take that second electron. Now, one magnesium is now an ion, right? Magnesium, the 2+ ion. And these 2 chlorines have been ionized as well, and they'll have the negative charge. So the formula from this, you use the ratio from your electron transfer here, and you'll end up with Mg, one magnesium, and then Cl2, 2 chlorines. That'll be your formula. Okay, so let's have a look at one that's a little more complicated here. We've got sulfur, and sulfur is in the 6th column, and it has 6 valence electrons. And then we got aluminum here, and it's in the 3rd column, or 13th column, and it has 3 valence electrons. So you can start transferring. Again, the transfer always goes from the metal to the nonmetal. So between the 2 of these, aluminum is the metal, so it's going to be the one that gives. So it's going to give 1 electron here. Great. Sulfur's not quite full yet. And so another electron is going to go over here. And now that sulfur is full. That's awesome. But the aluminum isn't quite done giving electrons, so it needs another sulfur to help it out. So I'll put another sulfur down here. And we'll give it this last electron. Awesome. Now that aluminum is all good. However, the sulfur isn't good. Uh-oh. Got to keep going. So I'll put another aluminum over here. Doesn't matter where you put it. And we will take this electron and put it on that sulfur. Great. Now that sulfur's done. But what about this aluminum? Keeps going. So one more sulfur should do the trick here. And here we'll put the other electron there. So we got one going here, and then one going here. And I think that means that everybody's taken care of. So we've got 3 sulfurs that are all ionized now, and we've got 2 aluminums that are ionized. So we got 2 Al, and it gets a +3 charge, and we've got 3 sulfurs, and it gets a -2 charge. So the formula for this, we're going to put the metal first, will be Al with a little 2 and an S with a little 3. That'll be the formula for this compound. Another interesting feature of ionic compounds is that once they're bonded, they have no charge overall. The positive charges will balance out with all the negative charges. And so you can use that as a sort of double check to make sure that you have made a compound that is, possible. So if we look at our first compound that we made in the previous slide, we have 1 magnesium and we have 2 chlorines. And the charge on the magnesium, if you look on your periodic table, in this column is +2. And the charge of the chlorines are each -1. And if we add all those up, you get 0. Ding, 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 we must have did it right. Here with the aluminum and the sulfur, we have 2 aluminums and we have 3 sulfurs. Each aluminum, if you look at the column on the periodic table, has a charge of +3, and each sulfur has a charge of -2. And if you add all those up, ding, 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 no overall charge. So that's like a little double check you can do for all ionic compounds. Okay, so our last way of finding a formula is called the crisscross method. In the crisscross method, first off, you write out the Lewis symbol for the ion. And so that means you give it a symbol and you give it a charge. And if the charge is a 1, you don't need to write the 1. You just put the plus or the minus. So an invisible 1 here. And here's oxygen, and so you can see the symbol, and it's got its charge. And so what you do is you take the numbers from the charge, and you crisscross them to make the formula. So the number of the charge for the oxygen becomes the quantity of sodiums in the formula. And the number for the charge of the sodium becomes the quantity of oxygens in the formula. And again, with 1s, you don't need to actually write them out. So let's try a couple of examples. So if you look up on your periodic table, you can see calcium in group 2, and so it's going to get a +2 charge. And you get fluorine in group 7, so it's going to get a -1 charge. And so you can crisscross the numbers. Remember, invisible numbers are 1s, so 1 calcium and 2 fluorines. For magnesium and phosphorus, if you look at where magnesium is on the periodic table, it's +2 as well. Phosphorus is in group 5, so it gets a -3. And so you're going to cross the 3 over to the Mg and the 2 over to the P. Remember, don't cross the charge values, the pluses and the minuses, just the numbers. So this one becomes Mg with the 3 and phosphorus with the 2. Ionic compounds also can be described with names, and so using the formula you can figure out the name pretty easily. You can see on this tube of toothpaste that there's sodium fluoride in there. They don't use the formula, they use the name for it. And so that means that there's sodium and there's fluorine. And so all they did was change the ending to IDE. And you can do that for all compounds that have 2 elements. So for our examples here, we have sodium again, only this time it's phosphorus, so you say phosphide. And we got magnesium. And instead of fluorine, you'll say fluoride, just like on the toothpaste. And for this last one, we got aluminum. And then for the last one, it's chloride. So just add on that suffix in place of the ending on the second element, and you've got yourself a name for your ionic compound, at least the simple ones. All right, so finally we can combine our skills here to be able to figure out what the formula is from a name. What you're going to do is you start off by writing the ion symbols with their charges. So we got calcium. Calcium gets a charge of +2. We've got chlorine. Chlorine gets a charge of -1. And then you do your crisscross to figure out the formula. And then one other thing we're going to add in here is if you can reduce, we should. All right, so we do our crisscross here. The 1 goes over there, the 2 goes over there. We end up with calcium and 2 chlorines. Great, that's a formula. Since this is the 1 and that's a 2, we can't reduce that any further because the 1 cannot be divided and still be a whole number. So let's look at this next one here. We've got calcium, which has a 2, and oxygen, which also has a 2. So if we crisscross these, we'll end up with calcium with the 2 and oxygen with the 2. But that can be reduced. Remember that the formula represents a ratio of ions in that crystal lattice. So if we can divide both of these numbers and make it smaller, then we should do that. So 2's obviously we can divide by 2, and you'll end up with calcium and 1 oxygen. So that is reducing. Finally, let's look at aluminum sulfide here. We got aluminum, it has a charge of +3. We got sulfur, it has a charge of -2. And you do your crisscross. We end up with Al2S3, and we can't reduce that anymore either. And so we're okay. We can leave that one as is. Okay, Hope you feel confident with all you've learned here about ionic compounds. See you soon.